Welcome to lecture number 2 on earth pressure theories. In the previous lecture, we have introduced to introduction to earth pressures which is caused by soil, and we also discussed in detail about earth pressure at rest and different conditions. In this lecture, you will be introduced to earth pressure theories. One of the earth pressure theories which we are going to discuss today is Rankine's earth pressure theory. And we discuss in this lecture about active and passive earth pressure states which are postulated by Rankine, and some relevant problems and extensions of this Rankine's theory for different cases in soil mechanics. Before venturing into this, let us review what we discussed. We discussed that the earth pressure coefficient K naught, which is found to be depend upon relative density of sand, process by which the deposit was formed, and the stress history. And we discussed that it is can be estimated by using Jackie's formula, which is for normally consolidated soils K naught is equal to 1 minus sin phi dash. For over consolidated clays, it is K naught is equal to 1 minus sin phi dash into OCR raised to sin phi dash. The K naught of normally consolidated clays is related to the plasticity index. According to Alpha 1967, we can also give a correlation between K naught and Pi. K naught is equal to 0.19 plus 0.233 log to the base 10 of plasticity index. And when we wanted to measure, say for example, you have got the K naught conditions in a basement wall and which is surrounded by say water in the soil, then let us see what pressures it creates on the wall due to the earth pressure at rest conditions and at because of the water. So here, because of the submergence, the unit weight of soil is equal to the submerged unit weight of the soil. And here the triangular linear distribution is for the earth pressure at rest, where P naught is the earth pressure thrust at rest, that is P naught, which is P naught is equal to half K naught gamma dash z square, where if z is the say depth of the case under consideration, and K naught gamma dash z is the earth pressure at rest. This earth pressure at rest is also has a component which is now due to water which is filled in the voids. So that pressure is equal to Pw is equal to half gamma w z square. As water is not having any shear strength, you can say that the Ka Kp is equal to 1. So with that Pw is equal to half gamma w z square. Now let us look into these earth pressure conditions and different possibilities. Let us assume that we have got a soil which is retained by a vertical wall. Let us assume that base and as well as the wall interface is smooth. So the base of the wall is assumed to be smooth and the wall is also assumed to be smooth. So these earth pressure problems which are indicated in this case, the soil behind the wall is called backfill, and this is wall which is shown here, a cross section diagram shown here. So these earth pressure problems are often dealt with plastic equilibrium in soil mass. So often these earth pressure problems are dealt with the plastic equilibrium condition in a soil mass. What is this plastic equilibrium? A body of soil is said to be in a state of plastic equilibrium if every part of it is on the verge of failure. So this is can be visualized by a perfectly rigid plastic model, where with a stress strain relationship, if you assume that it is rigid and perfectly plastic. So here a graph which is shown shear stress versus shear strain, and at a zero shear strain itself, it actually attains the that yield shear stress. So, here the stress strain behavior of the soil can be represented here by the rigid perfectly plastic idealization. That means, here yielding and shear failure both occur at the same state of stress, and unrestricted plastic flow takes place at this stress level itself. So, this particular state is actually it is indicated here by y dash, is actually said that it has reached the plastic equilibrium. So, a soil mass is said to be in state of a plastic equilibrium if the shear stress at every point within the mass reaches the value represented by a point y dash. So, this plastic equilibrium can arise if there is a movement of the wall either away from the fill or towards the fill. Suppose in case if the wall is at rest, then elastic equilibrium conditions prevail. That is what we discuss, and we define that as coefficient of earth pressure at rest, K naught. So, Rankine in 1857, the Rankine's earth pressure theory is postulated after Rankine in 1857, and he assumed the following way. The soil mass is assumed to be homogeneous and dry and cohesionless. That is the first assumption which was put forward by Rankine. And ground surface is plane, which may be horizontal or inclined. So, the ground surface is initially backfill surface is assumed to be plane, and then later it has been extended to inclined cases. Face of the wall in contact with the backfill is vertical and smooth. That is, the back of the wall, that is the wall which is in contact with the soil, the interface is assumed to be smooth, that is frictionless condition, which indicates that the wall is having a zero shear stress along the interface. So, this particular condition with the horizontal backfill and with frictionless interface at the soil and wall interface is referred as also as Rankine wall. And another important state which he defined is that the possibility that the wall moves away from the fill, and that particular state is actually defined as an active state, and if the wall moves towards the fill, then it is actually defined as a passive state. The wall yields about the base sufficiently for the active pressure conditions to develop, and if it is passive case, that is under consideration, the wall is taken to be pushed sufficiently towards the fill for the passive resistance to be mobilized. So, which we are actually going to discuss these states, active states and passive states, which are actually Rankine's states of plastic equilibrium conditions which are put forwarded. So, one is called active, which will actually arise when the wall moves away from the backfill, and the passive state can arise if the wall is pushed towards the backfill. Now, consider earth pressure states like what has been told in the previous slide, like wall moving away from the backfill and wall moving towards the backfill. Here, the wall movement away from the backfill is actually shown here in this cross section. It is a backfill here with a horizontal surface, and the friction between the wall interface and the soil is 0, that indicates that smooth, and that is this is idealized by a Rankine wall, and assuming that the wall the base roughness is very smooth. So, with that you can actually get a uniform movement for the wall. So, in this case a wall movement away from the backfill by a distance say by a displacement say delta h, which moves away from the fill, then that actually arises a case that is referred here as active case. If the wall is pushed towards the backfill, then that is referred as passive case here. So, earth pressure states here which we define at rest condition, that is condition of elastic equilibrium condition, where the wall is at rest condition, that is no movement, that is zero strain condition, which is seldom which is next to impossible to maintain this state. So, possibility of the active and passive states are always there. So, in the earth pressure states, now wall movement away from the backfill, if you consider, the conditions are same as what we discussed earlier. Now, consider an element here at a depth z, which is having vertical stress sigma v and horizontal stress sigma h. So, and these surfaces being horizontal, you can see, and these stresses can be called as principal stresses, and if the sigma v happens to be the major, then it is called major principal stress, and sigma h if happens to be minor, then it happens to be called minor principal stress. So, soil element at any depth z is subjected to a vertical stress sigma v and a horizontal stress sigma h, and since there can be no lateral transfer of weight if the surface is horizontal, and we can say that the shear stresses are absent here. So, no shear stress exists on the horizontal and vertical planes. So, vertical and horizontal stresses are here, we can call them the planes on which these vertical and horizontal stresses sigma v and sigma h are acting can be called as principal planes. So, a case where what will happen to these sigma h and what will happen to the sigma v when the wall movement away from the backfill, and that we will see and discuss in the next slide. So, in case say if there is no movement, then that condition we referred and then said as at rest condition K naught. At rest condition is defined as a state of 0 lateral yielding, and if there is no lateral strain, then epsilon is equal to 0. And this condition, if you look into the tau sigma plot in a Mohr circle plot, you can see the Mohr circle is at rest Mohr circle is here, where sigma v is represented here and sigma h is represented here. So, this is sigma v and this is sigma h naught. So, the K naught, which is nothing but sigma h naught by sigma v, which is the coefficient of the pressure at rest. So, we can say that this, if this happens to be the shear strength envelope, which is the failure envelope, and which indicates that the circle is stable and yet to attain any failure. So, we can say that is a stable equilibrium condition, and that is why we say that at rest condition it actually remains in the elastic equilibrium condition. Now, a case where when the wall movement takes place and then which is away from the backfill. In the previous case, previous slide what we saw is a 0 strain condition where wall is a non-yielding wall, and this type of conditions can arise particularly if you have got a basement wall which is propped at the beam connections and if it is having a backfill which is filled, then that condition may be very similar to the at rest condition. So, at active state, in this case consider a wall AB which is again smooth and a base having a smooth nature, and wall movement occurs away from the backfill. And here again the element which is considered is sigma v and sigma h at a depth z. Now, if there is a movement of the wall away from the soil, then sigma h decreases. Please note down the horizontal stress decreases as the soil dilates or expands outward, the decrease in sigma h being an unknown function of lateral strain of the soil. So, the decrease in sigma h being an unknown function of the lateral strain of the soil. So, here as the wall moves away from the backfill, the soil dilates or expands outward. So, this condition what will happen is that when the wall movement is being taken place, then it is actually opposed by the shear resistance offered by the soil. So, in this case what will happen when the wall movement takes place, the strains develop, these strains mobilize the shear stresses, and with that what will happen, the soil offers its resistance and tries to restrain the movement. So, in the process what will happen, the horizontal stress which was there drops down to a minimum value. So, the state where it reaches the failure, then we can say that the active state of failure or active state of plastic equilibrium condition has attained. So, if there is a movement of the wall away from the soil, sigma h decreases as the soil dilates or expands outward, the decrease in sigma h being an unknown function of the lateral strain of the soil. If the expansion is large enough, then sigma h decreases to a minimum value such that the state of plastic equilibrium develops. So, that is what we have discussed. If the expansion is large enough, sigma h decreases to a minimum value such that the state of plastic equilibrium develops. So, since active state is developed by a decrease in sigma h, this must be a minor principal stress, and that vertical stress sigma v is the major principal stress. So, here if you look into here, this is the minor principal plane because sigma h is being is decreasing. That the reason for the decreasing is that because the movement is opposed by the resistance, shear resistance of the soil. So, because of that there is a decrease in the sigma h. So, sigma h, the active state is being developed by decrease in sigma h, the sigma h becomes minor and the sigma v becomes major. So, in this case here with the surface being horizontal, what we can say, this can be a major principal plane and this is a minor principal plane. So, sigma h when it reaches to the active state, the horizontal stress becomes sigma a, that is the minimum value where it has actually attained a state of plastic equilibrium. Now, let us consider the second case or state what we discuss is passive state. This case, wall moves towards the backfill. Again the surface, ground surface is horizontal, AB is the initial position of the wall and A1 B1 is the wall after pushing adequately towards the backfill. So, in this case again same element, but same depth z, sigma v and sigma h being the sigma h is the horizontal stresses, sigma v is the vertical stress. So, if there is a movement of the wall towards the soil, there will be lateral compression of the soil and the value of sigma h will increase until a state of plastic equilibrium is reached. So, here if there is a movement of the wall towards the soil, there will be lateral compression of the soil takes place. In the previous case, when the wall moves away from the backfill, there is a lateral expansion has taken place. In this case, when the wall moves towards the fill, there is a lateral compression is taking place. So, the value of the sigma h will increase until a state of plastic equilibrium is reached. Here, the wall movement is again is opposed by the shear resistance along the sliding rupture plane. Since the passive state is developed with an increase in sigma h, this must be a major principal stress and vertical stress sigma v is the minor principal stress. So, sigma h value increases and even it crosses the sigma v value. So, sigma h now becomes the major principal stress and sigma v becomes the minor principal stress. But in both active states and passive states at a particular depth, the vertical stress remains constant because the weight of the soil which is involved in the process is same. So, at a particular depth, if z is the depth, the weight of the soil which is involved in this process of active states and passive states being same, the sigma v remains same. But only the changes which occur is in the lateral stresses, that is horizontal stresses sigma h. In one case, what will happen is that when the wall moves away from the fill, there is a decrease in the sigma h. When the wall moves towards the fill, there is an increase in the sigma h. So, let us consider the state of the elastic equilibrium conditions and then state of plastic equilibrium conditions, when these things can occur, and then local states of plastic equilibrium conditions. So, in this slide what you are seeing two diagrams, and in case if the wall is at rest condition, then we see this type of rupture lines or slip lines which these lines indicates the zone of elastic equilibrium conditions. So, entire soil when is at rest condition, it actually having k naught is equal to sigma h naught by sigma v and which maintains this elastic equilibrium conditions. Suppose if the wall moves away from the backfill and say if AB is the original position of the wall and it moves to A1 B1 new position, say by distance constant distance d1 across the depth. Then what will happen? Entire soil mass reaches this plastic equilibrium state, provided if there is a smoothness at the that is if the surfaces are smooth at the base as well as at the interface. So, in such situations that is possible, but it is next to impossible to have that condition, like in such conditions like in a walls, retaining walls resting on soil, because of the roughness at the base, there is a possibility of local states of plastic equilibrium to develop. So, a certain state, the zone in which actually the plastic equilibrium or a sliding wedge or a sliding entire failure wedge develops, the remaining portion of the soil remains in a state of elastic equilibrium condition. So, here the top diagram which is shown, which is active Rankine state in sand contained in a rectangular box. So, what you see here, this particular portion which is actually is nothing but the failure wedge, and these are nothing but the slip lines. what you are seeing, these are slip lines, and these slip lines, because soil being homogeneous, we can have slip lines in both the directions. So, you can see that this direction, the slip lines are indicated, and this line inclination, which is actually indicated by 45 plus phi by 2, 45 plus phi dash by 2. So, due to the roughness at the base, when the is possible that here the lateral displacement is 0 at the toe of the wall, and then at the crest actually it can move by a certain distance. So, in such situation, when the wall yields about its base, the condition can prevail if there is a roughness at the base. In that situation, there is a possibility of local states of plastic equilibrium to develop. So, active Rankine state in sand contained in a rectangular box with a roughness at the base. And another case, if the wall moves towards the surface, if the wall moves toward the soil, that is backfill, in such situation the passive Rankine state contained in sand in a rectangular box, here the wall actually have to be moved adequately so that this condition occurs. So, here you can see that the failure or rupture planes or sliding wedge is actually inclined at 45 minus pi by 2 with the horizontal, that is indicated and shown here 45 minus pi dash by 2. And here wall is actually, because of the roughness at the base, is displacement is 0 here, and here is actually having a movement or rotation towards the backfill. In such situation, then this is the portion which is actually undergoing have undergone the failure, and then this is called also a failure wedge, and these are slip lines in both the directions. So, in passive Rankine state, which is shown here with a local state of plastic equilibrium, and as well as in the active state with a local state of plastic equilibrium. Now, a case again, let us consider active and passive earth pressures. Here in this case, in the slide which is shown here, in cohesionless soils, basically for granular soils, if the wall actually moves towards the backfill, you can see that here in this zone, say particularly for element A, which is going to come here, which actually observed to have experienced lateral expansion. So, here wall moves away from the soil here, and which actually has got the deflection here, which indicates that the wall moves away from the soil. In this case here, this part of the zone, and this actually wall moves towards the soil. So, this particular type of wall which is referred as cantilever sheet piles, which we are going to discuss later. But here at point A and point B, if you observe here, in this case the wall moves towards the soil and is actually subject to, this is called a passive zone, and in this case if it is rotated about it the toe, then actually here this is subjected to wall moves away from the soil. Once again we look into this. So, this is a smooth wall with wall at the interface and subjected to deflection. Now, you can see that the expansion which has taken place and which induces a lateral expansion, and the sigma h now tends to become sigma a, and that is actually called active earth pressure. And here in this case the wall moves towards the soil, where the passive condition is represented here. So, these active states and passive states can occur in, say, in cantilever sheet pile walls, suppose if you are retaining the soil, and that it can occur behind the wall, it can be subjected to active state, but at the below its dredge level it can be subjected to passive state. And these two, when they are in equilibrium condition, they actually maintain the stability of the wall. So, element A, if you consider location of the failure plane is at 45 dash phi by 2, 45 plus pi dash by 2. This you would have already acquainted from the shear strength lectures. So, sigma V is the major principal stress, and this is the major principal plane, and sigma H is equal to sigma A, which is nothing but active earth pressure, and which is this is the minor principal plane. So, here in this slide we have tried to demonstrate the active and passive states. The categories of lateral earth pressures, now if you summarize, first condition is that at rest case, that is no movement condition, that is zero strain condition, then it actually induces K naught is equal to sigma H naught by sigma V, that is at rest condition. Another case which we have discussed is active case, wall moves away from the soil. In this case, wall moves towards the soil, that means that wall moves into the soil or towards the soil, that is nothing but a passive state. So, now we need to look into it, retaining wall movements and related states of stress. So, if you look into here, this first condition what we represented is the at rest condition, that is that is state condition, and that is zero strain condition. And here this from K naught to Ka, that now that coefficient earth pressure coefficient of earth pressure at rest now can no longer be coefficient of earth pressure at rest, it changes to Ka, and that is referred as coefficient of active earth pressure, Ka. And it is now that Ka which is formulated is a function of the say friction angle and conditions like wall surface horizontal and smooth interface, and Kp is the coefficient of passive earth pressure. So, this is the deflection, wall deflection towards the backfill. So, if you are retaining a soil wall again along a certain highway, and then if the wall actually tends to move away from that, then actually it can present active state, and this is the example where how when the wall moves towards the backfill can induce a passive condition. So, possible wall deflection related range of lateral earth pressure coefficients are shown here. Suppose if there is wall rotation takes place here, and in this case active case, and here at this case if there is a soil compression is taking place, then there the passive state can mobilize. In active earth pressure and in cohesionless soils, particularly for granular soils. So, what we have seen here is that sigma V dash, that is at a particular depth z, and sigma h dash, that is a horizontal stress, which is sigma h dash is equal to K naught sigma V dash, which is nothing but K naught gamma z, because z and gamma is the unit weight of soil. Now, as the wall moves away from the soil, sigma V remains the same, that we discussed, because the weight remains the same, the soil which is actually participating is weight is same. So, with that sigma h decreases till failure occurs. So, what we have seen is that in active state the sigma h decreases till failure occurs. So, now let us represent this state in active earth pressure condition, but particularly in tau sigma condition with Mohr circle. So, as the wall moves away from the soil, so initially this condition is called K naught state, that is coefficient of earth pressure at rest case. But as sigma h decreases, if this happens to the failure envelope for a soil having a friction angle phi dash, then we can say that the moment it actually comes in contact or tangential with this failure envelope, the soil attains failure. That means that it has reached the plastic equilibrium state. So, in this case, when you look into here, the decreasing sigma h dash is taking place from here to here, and moment it attains here, that sigma h dash becomes to sigma a, that is the minimum value, that is the active earth pressure condition. So, here this condition of series of Mohr circles are possible with sigma v dash as constant. With that, what will happen is that slowly gradually the wall attains failure, and it comes in one moment it comes in contact. Similarly, if you have got a C phi or a say C phi soil, then what will happen, the failure envelope will be there like this, and that becomes the concepts are same, but here actually being introduced for a cohesionless soil or granular soils. But if it is a C phi soil, the failure envelope will be here, and then the state will be initially K naught state circle, Mohr circle will be here, and then comes in contact with the moment it comes in contact with the failure envelope, it attains failure. Soil said to be in the active state. Now, this once again let us look into it. So, this is active the Mohr circle tau sigma plot which is shown here, and here this is the sigma v, which is the vertical stress which we know. So, from the Mohr circle fundamentals which you have studied in your shear strength, from the known state of stress on a Mohr circle, when you draw a line, extend a line to the other part of the Mohr circle, and that is we can locate that point as a pole. In this case, the pole is on the left hand side here, which is for the active state here, and this is the a failure plane for a C phi soil having C and phi, that is cohesion and friction angle. So, intercept here is C dash and is friction angle is phi dash. So, this is when the sigma h decreasing, that means the initial Mohr circle somewhere here, and then it actually change it or decrease it up to sigma h dash decreasing up to sigma a and attains failure plane. So, this Mohr circle is developed, this is nothing but a failure Mohr circle at the active state. So, Rankine's theory of earth pressure in the active state, when you represent in Mohr circles, it is how it looks like this. Now, the same that means that here these element, each and every element here attains failure and attains plastic equilibrium condition, means that they attain failure and reaches the active state of plastic equilibrium conditions. So, here this is the condition is represented. So, this failure plane, which is when you draw a line from here to this point, to the point where it cuts the, this point cuts the failure envelope and join this inclination is nothing but theta, which is nothing but 45 plus phi by 2, that is 45 plus phi dash is the friction angle, 45 plus phi dash by 2. So, as if the soil is homogeneous, it can have a failure plane like this, it can have a failure plane like this. So, this failure plane actually represents this failure plane which is here with this. Now, let us try to look into how to arrive at this magnitude of active earth pressure. We have introduced the concept of the Rankine's active earth pressure of when it actually attains state of plastic equilibrium condition. Now, consider the same like in the previous case, what we discussed is that this is a Mohr circle in a tau sigma plot, it is a failure Mohr circle. So, here for upper part as well as lower part of the Mohr circle is shown. So, in this next slide we have considered only in a tau sigma plot where only the upper part of the Mohr circle is shown, and here this is again a failure envelope with the phi dash being the friction angle of internal friction, and sigma v dash is the vertical stress at a depth z, it is nothing but a gamma z, and sigma h dash active is nothing but sigma a, which is active earth pressure. So, when this Mohr circle is having points intersects at sigma axis at A and at point B at the failure envelope and at point C at the center of the Mohr circle. So, from the geometry conditions, we can say that sigma A is equal to OC minus BC. Sigma A, which is this one, is nothing but OC minus BC, which is nothing but this distance. But from this condition, from this triangle OBC, we can see that BC is equal to OC sin phi dash. So, now write substitute here for BC is equal to OC sin phi dash, that is sigma A is equal to OC into 1 minus sin phi dash, and similarly sigma V dash we can write this stress is nothing but OC plus BC. Now, BC is equal to OC sin phi dash. So, with that we can say that sigma V dash is equal to OC plus BC, which is nothing but OC sin phi dash, which we can be written as OC into 1 plus sin phi dash. So, now the ratio of sigma A by sigma V dash, which is nothing but 1 minus OC minus BC divided by OC plus BC. So, OC and OC will get cancelled. So, what we get is that sigma A by sigma V is equal to 1 minus sin phi dash by 1 plus sin phi dash, which is nothing but tan square 45 minus phi dash by 2, which is actually indicated by K suffix A, which is nothing but a coefficient of active earth pressure. Now, sigma A is equal to, now we can write sigma A is equal to Ka by sigma A is equal to Ka into sigma V dash, because sigma A by sigma V dash is equal to Ka. So, sigma A is equal to Ka and sigma V dash. So, sigma V dash is nothing but at a given depth gamma z. So, at depth z is equal to 0, then it becomes sigma A is equal to 0. At depth h, say z is equal to h, then sigma A is equal to Ka gamma h. So, for where the coefficient of active earth pressure is indicated by Ka, say for phi is equal to phi dash is equal to 30 dash with K, sigma A with Ka is equal to 1 minus sin phi dash by 1 plus sin phi dash, we get Ka is equal to 1 by 3, that is nothing but 0.333. Similarly, for the passive state, if you consider, this is a initially K naught state, and this is the failure envelope, and here in this case the wall moves towards the soil, So, you can see that when the wall is moved towards the soil, it tries to attain and reach the failure surface, but in this case the sigma h naught, which is initially coefficient of horizontal earth pressure at rest, which is actually changes to sigma p by increasing. So, it happens like this with the same sigma p dash, sigma v dash, these Mohr circles propagate towards the right and attains the failure. So, initially the sigma h dash now which is changed down to sigma with increasing sigma h dash reaches to sigma p, that is nothing but a passive earth pressure. So, here the failure condition which is wrongly shown here, which is failure passive state, which is actually indicated by a passive earth pressure. Now, the condition similarly like what we discussed in case of active condition, similar way we can derive also for passive earth pressure conditions in cohesionless soils. So, here the same element is taken sigma v dash. Now, sigma v dash which is the vertical stress, sigma v or v dash the effect vertical stress, and sigma p is the horizontal stress which is at passive state, that is the passive earth pressure. Now, this is that Mohr circle at failure. So, sigma v dash is here and which is minor principal stress, and the sigma h dash passive is equal to sigma p is the major principal stress, and with this now this becomes the major principal plane, that is this is the major principal plane which is actually shown here. This is the major principal plane and this is the minor principal plane, this horizontal is the minor principal plane. So, sigma v dash vertical stress is acting on the minor principal plane, and this being the now this is the known point for us, and when you draw from the known state of stress to a point on the Mohr circle, and this becomes the pole in case of passive state. So, here from the in the case of active state what we did is we drawn from here to here and tried to represent this, and these being major and this actually is now major principal plane, and this being minor and this actually is a minor principal plane here, and here the failure plane is indicated here 45 plus pi by 2 at the point where it touches with the failure envelope. The failure plane is at 45 plus pi by 2 with the horizontal. Similarly, here which is shown for passive earth pressure condition, and attains passive state of plastic equilibrium with increasing sigma h dash. Sigma h dash changes to sigma p. Now, with this now from again similar conditions like sigma p is equal to now we can say OC plus BC, that is OC plus BC here, BC is equal to OC sin phi dash, BC is equal to OC sin phi dash, with that sigma p is equal to OC into 1 plus sin phi dash, sigma v dash is equal to OC minus BC, with that OC into 1 minus sin phi dash. So, the ratio of sigma p by sigma v dash is equal to OC plus BC by OC minus BC, which actually turns out to be sigma p by sigma v dash is equal to 1 plus sin phi by 1 minus sin phi is equal to tan square 45 plus phi dash by 2 is equal to Kp, where Kp is the coefficient of passive earth pressure. Now, passive earth pressure which is now indicated as sigma p is equal to Kp sigma v dash, where sigma v dash is equal to gamma z at a depth z from the ground surface. So, in case of passive state, Kp is defined as coefficient of passive earth pressure. Say for phi is equal to pi dash is equal to 30 degrees, Kp is equal to 3. This is wrongly indicated, which is 3. So, Mohr circle at rest, active and passive states which are combinedly represented in a tau sigma plot. So, this is the same soil which is having a failure envelope and which is having a coefficient of the angle of internal friction is 30 degrees, and this is the failure Mohr circle, and this is the initial Mohr circle, that is the at rest state, and once it attains this failure which actually changes to active state Mohr circle. So, here from here sigma h z dash is the vertical stress at a depth z. So, from this point when you draw a line to the other point in the Mohr circle, the other end in the Mohr circle, and that point becomes the pole for active state here, which is shown here with a highlighted portion, and CD is the failure plane inclination which is nothing but 45 plus pi dash by 2 here. So, sigma x dash is equal to sigma 3 dash, nothing but the minor principal stress is equal to sigma a dash is nothing but Ka times sigma z dash, which is nothing but coefficient of active earth pressure times sigma z dash. So, water, if you compare the water and solid, water and soil has got some resemblance. Like water, it exerts lateral earth pressure. So, as we discussed in the previous lecture. So, here we can say that which is nothing but Ka times sigma z dash, it actually transfers, where Ka is the coefficient of earth pressure in active state. Similarly, Mohr circle which is shown here is for passive state, where sigma z dash is the vertical stress, and this is the Mohr Coulomb failure plane. And when you draw a line from the other end of to the other end of the Mohr circle, you can say that we can locate the pole for the passive state. From here, from E, if you draw a line to the failure envelope, then it intersects at F, then this nothing but the angle of inclination of a failure plane in case of passive state, that is 45 minus phi dash by 2. So, in this case also it is possible if the soil is homogeneous. So, in this case also a failure plane can be possible if the soil is homogeneous. So, here in this slide combinedly in Mohr circles at rest and active and passive states. So, this Mohr circle is for at rest condition, and this Mohr circle is for active state condition, and this Mohr circle is for the passive state condition. Now we have discussed two states, active states and passive states, and when you look into it, K naught is actually greater than Ka. So, when then we should ask ourselves, shouldn't we design retaining walls to resist at rest than active case at pressures, since the thrust on the walls is greater than the K state. That means that do we need to design walls for earth pressure at rest conditions? But if you look into this, the next forthcoming slides will answer our question. So, our question is that should we design retaining walls to resist at rest than active earth pressures, since the thrust on the walls is greater in the K naught state. Because if you look into it, the K naught is actually greater than Ka, which indicates that at a particular thrust, if you compute with Pp, that is P naught, that is the active the thrust at the rest condition, which is half K naught gamma h square, which will be more than half Ka gamma h square, which is the thrust due to an active state. Now, if you look into it, this is in cohesionless soils, sigma h dash, which is in the K naught state, but with a little movement, as the wall moves away from the soil, sigma h decreases until failure occurs. So, very difficult to, it is next impossible to maintain these conditions. Also, it will become unconservative to actually design for these conditions. So, except in some special cases like a basement walls when they are subjected, and such type of conditions where K naught conditions and you are sure that they prevail, then they can be designed for that more pressure. But otherwise, when the cantilever wall or is a cantilever sheet pile wall, a retaining wall retaining the soil, and in that case they have to be designed for active state when they are subjected to for attaining this active state. From the next slide we can see that a minimum movement is sufficient to actually reach that active state. So, it is seldom impossible to actually maintain that K naught conditions. So, which is actually it is not unwise to it's not wise enough to actually design and have a conservative design. So, it is actually designed for active state only. So, as the wall moves away from the soil, sigma h decreases till failure occurs. So, this is the K naught state, and with the wall movement, as you can see that it actually attains an active state and it is maintained. The relation between lateral earth pressure and movement of the soil, if you look into it. For example, if h naught is the height which is undergoing say lateral movement here, say K condition which is shown here, and the wall actually is at rest condition, that means here this is the portion. Now, the active condition can occur when wall actually rotates about the toe. That means that if the rotation is nothing but delta x by h naught. So, say gradually the wall yielded away from the backfill or rotated about the backfill. So, in such situation you can see that the active condition actually occur with a 0.5% strain only, with very low strains. But whereas in case of a passive condition, much larger movements are required. So, that is in case a type is also function of type of soil, like dense sand or loose sand, like in the soil states particularly 2% strain for dense sands and 50% strain for loose sands. So, if the strain which is the compressive strain, if it actually reaches 15% or so for loose sands, then actually it will actually attain the passive condition, whereas in case of say dense sand, it actually is required only 2% strain. So, keeping this in point of view, actually we actually design the walls for active state condition only. So, here in this diagram what we have seen is the delta X by H and K, that is the lateral earth pressure coefficient. So, here much larger movements are required for passive condition to be developed, and here very little movements are required to actually attain these active conditions. So, keeping this point of view, actually we design the walls for the active pressures, and in case if there is a passive state arises like bridge abutments, when they are abutments when they are pushed towards the retained soil, then the condition of passive state occurs there at that particular site. These type of conditions like what we discussed, like development of this rupture planes, all these things can be also demonstrated through physical model experiments. So, in this case a photograph demonstration experiment which was carried out in the physical modeling experiment high gravities at IIT Bombay is shown. Here what you can see is that this is a cantilever retaining wall having a active state at the top, wall movement away from the backfill, and this is the passive state which is actually embedded here. So, here is a model cantilever wall, and this is a soil which is nothing but a sandy soil in dry state and having a residue density about 55%. Then wall yielded and rotated yielded about a certain point here and moved away from the backfill. So, in the process what you can see, the development of these lines are nothing but sand marker lines. So, these lines you can see that they cut into number of planes, and these planes indicate that these rupture planes which are developed, they are nothing but which we discussed in the previous case. As the wall moves away from the fill, you can see that the soil followed the soil followed the wall and settled in this case and induced the rupture planes. So, here in this you can see that because of the condition here represented, this particular state is actually a plastic equilibrium state. The rest of the state is here the elastic equilibrium still remain. So, these are high gravity experiments which are carried out at IIT Bombay by using National Geotechnical Centrifuge facility available at IIT. So, in this case the soil is not yet reached the passive state. So, the sand marker lines remains intact. So, this is another view of the same model. This is the deflected wall, you can see the wall deflection, and you can see here the formation of slip lines. In these zones it indicates that the plastic equilibrium has developed, the soil has actually attained the failure and the active state has reached. And this is the outward movement of the wall. This is the wall was initially here and moved in this direction. So, in the process what will happen, you can see this cut like the bench like formation or deformations of at the top, they indicate that the movement or a settlement of the wall, settlement of the backfill soil. So, these are shown just to see how the demonstration experiments can be carried out and also to understand the concepts what we discussed just now, like active states and passive states. So, when the wall which is say a smooth and a backfill surface is horizontal, then we refer that as a active wall, and with that actually two states are possible. One is active state and another one is passive state. The passive state can occur when it is wall movement takes place towards the soil, and active state can occur wall movements takes place away from the soil. So, in the process when the wall moves away from the backfill, with that there is a lateral expansion takes place. The sigma h dash which was initially at rest the horizontal pressure reduces to sigma a. So, the reduction is actually due to resistance offered by the soil against the wall movement. And in this case of passive state, when the wall moves towards the soil, so such situation again the soil offers the resistance, that is the resistance or the strength in the soil offers the against the movement. So, with that the sigma h dash has to mobilize more. So, it reaches to the passive state, which is nothing but a passive state of plastic equilibrium, and that pressure is called sigma p, which is coefficient of sigma p is the passive earth pressure. So, now if you have got a wall of height h, when the wall movement takes place away from the backfill, and at top the earth pressure is 0, at bottom the earth pressure is Ka gamma h, and in the case where if it is dry condition, and the lateral active thrust is of Ka gamma h square acting at h by 3 from the base. In the case of passive, if the wall is actually of having height h and the movement takes place towards the soil, then the total passive thrust is of Kp gamma h square, and Kp gamma h being the passive earth pressure at the base and 0 at the top. With that, what will happen is that the passive earth pressure test is of Kp gamma h square acting at h by 3 from the base. Now, if you we can extend these theories to a number of cases, like wall in submerged case with surcharge, without surcharge, and walls which are having cohesive soils and combination of layered soils. So, with that we can actually use and calculate the earth pressures, and once we get these earth pressures, and these earth pressures can be used to design the retaining structures. So, these are the inputs what we are studying, which is actually helpful in arriving at in designing the retaining structures.